That's me. That's one of the deadliest cancers in the world, and that's a website I made to solve it. But there's a catch. That's not just a website, it's actually a deep learning model that I created, which can both detect and predict the recurrence of NSCLC, the most common type of lung cancer. And it's like a huge problem right now. But why is that? Well, in 2020, there were over 2.2 million cases of lung cancer worldwide, with NSCLC being the most common of them. In fact, NSCLC accounts for 80 to 85% of total lung cancer cases. That means that in the US alone, there is someone diagnosed with NSCLC every 2 minutes. And the reason why boils down to two main factors. We can't detect it early enough, and we can't predict when the tumor will recur. Around 70% of the cases of NSCLC are diagnosed after the tumor has separated from its original location in the body, or it's metastasized. This makes treatment extremely difficult. Even non-smokers are at risk of getting NSCLC. In fact, that's 20% of the population that actually is diagnosed with NSCLC, which means that even you can get it as well. As with many cancers, NSCLC grows very slowly, meaning that symptoms only occur in the later stages of the disease. And when symptoms do occur, they're like any other respiratory disease, which leads NSCLC to often be misdiagnosed. But like I said, early detection is not the only issue here. It's been clinically proven that after treatments like chemotherapy, radiation, and surgery, a tumor can come back, even more aggressive than before. And this is what happens to 30 to 50% of the cases with NSCLC. Especially with treatments like surgery, a surgeon can only remove what he or she feels or sees. That means that micrometastatic cells are oftentimes left in the body. These cells can grow undetected and become even more aggressive than before. This means that out of the total number of cases of NSCLC, that's around 1 million people who have to go through the same treatment again and face death even closer this time. And the solutions we currently have in place are not sufficient. And this is where I come in. That's why, for the last few weeks, I've been building what I call recurvision.ai, a fully functional web application which is powered by a deep learning model that can both detect and predict the recurrence of NSCLC. And this deep learning model is powered by a convolutional neural network and a support vector machine, or SVM for short. First, let me explain how the convolutional neural network actually works. Now, our big brains are able to see images in their full color, or RGB, and are able to extrapolate different patterns to classify these images. But if a computer looks at these images, it'll get really confused. Now, the input for this model are CT scans. You can find them in the description, which are already somewhat black and white, but the computer will need to convert them to grayscale in order to remove any color discoloration and to remove any distractions. This is what we call pre-processing. After these images are pre-processed, we can feed them into the convolutional neural network. A convolutional neural network, or CNN for short, is an artificial neural network that specializes in classifying images. And it differs from a normal neural network because it has 3 distinct layers: the convolutional layer, the pooling layer, and the fully connected layer. The purpose of the convolutional layer is to detect certain patterns, features, or edges that'll help it classify these images. This layer applies filters, also known as kernels, to small regions of the input image, and it moves these filters across the entire image. This is what we call a convolution. Each filter learns to recognize specific patterns, and the output is a feature map. The pooling layer follows the convolutional layer. Its primary function is to reduce the spatial dimensions of the input volume while retaining important information. Pooling is achieved by taking the maximum or average value within a small region of the feature map. And this process helps to make the detection of features invariant to scale and orientation changes. And the fully connected layer is where all the individual layers, or all of the neurons in the neural network, all come together for the classification. This layer combines the features learned in all of the previous layers to make predictions about the input. And at this point, there are 4 main outputs: adenocarcinoma, large cell carcinoma, and squamous cell carcinoma, which are all NSCLC variants, and no NSCLC. Once the model was trained over 50 epochs, it achieved an accuracy of around 80%. Now, something that scientists are really missing out on when tackling lung cancer is predicting the tumor recurrence, which my second model aims to solve. Look, it's not like a doctor can just look at a patient and magically say there will be tumor recurrence in this patient. Tumor recurrence can only be calculated with a specific set of parameters, and even then, it's quite difficult for doctors to actually do. And so we can use a support vector machine, or SVM for short, to simplify this whole process. Each point in my dataset is plotted in an n-dimensional space, with its coordinate features being specific parameters like pack years or even age. Now, at a high level, SVMs classify objects by drawing a linear hyperplane, or what we call a decision boundary, to separate these data points into different classes or categories. In our case, recurrence or no recurrence. The ultimate goal of SVMs is to maximize the margin while minimizing the decision error. The margin is the distance between the hyperplane and the closest data points from each class. In simpler terms, it's just how well the classes are separated from each other. And a high margin equals a high confidence in classification. Now, for a dataset, you may be wondering, a lot of the values for each parameter are not specific numbers, they're words. Now, I think anyone would know that you can't plot words, so I had to label and code these values in order to convert them into numbers. Now, no, a lot of these parameters are not actually used because they're not needed for a classification. I use the fit transform method to assign a specific integer to each value in each category, something the computer can actually use. And now our support vector machine is able to draw a hyperplane and classify each of these patients as having recurrence or no recurrence. Now, although a small project, these models actually have huge potential to save lives. There's close to nothing like these models, and the reason why these models are actually so effective or could be effective is because of the amount of parameters/factors that they actually take in, especially the tumor recurrence model. Now, instead of doctors needing to guess treatment plans for a patient, they can now optimize them with these models. They'll know exactly whether or not a tumor is actually there and when it'll recur. That means that after surgery, a doctor can advance chemotherapy or radiation treatment so that they can prevent the tumor from actually recurring. In short, this model has the potential to transform the way that doctors treat NSCLC and even lung cancer in the future. The survival rate for NSCLC will not go down anymore, it'll go up. Now, with the disease as deadly as NSCLC, patients are just given 3 to 6 months to live after the tumor has metastasized. That means that every day towards treatment plans count. And a tool like recurvision.ai has so much potential to transform these treatment plans and result in greater patient outcomes, giving patients a much brighter future for their lives. Now, if you're still here, if you want to check out the full code and an article where I actually break down the issue further and the code itself, check the links in the comments, and I'll see you next time.